Hi, I'm Gabrielle Moore. I am in Lab Section 3, and I'm doing the video lab report for Experiment 6, which is also determining the concentration of citric acid found in lemon juice. So to start off today, we're going to start by writing the balance equation. So for neutralization reactions, the balance equation is going to be produced by an acid with a base to produce a salt and water. So the acid we're using today is going to be citric acid, which is found in the lemon juice. So the compound for this is going to be C3H5O, and then COOH3, and then typically for acids, the H is actually at the beginning, but for this one it is found at the end right there. This is an aqueous solution. So this is combined with our base, which is sodium hydroxide in this one, or NaOH. This has a positive 1 charge, this has a negative 1 charge, so that is set. This is also an aqueous solution. And then these two are going to be used to produce a salt, the sodium citrate, in our case, which is Na3, C3H5O, COO. And then this is also an aqueous solution. And then lastly, it'll be combined with, as I said before, our water, which is a liquid. Okay, so to balance this equation, I need to get this Na even with this Na, sodium. So we have 3 here, so I'm definitely going to need to put a 3 here. And then this is going to set me at 3 oxygen, so therefore I'm going to need a 3 here. And then with that, this is going to give me 3 H's, and I also have 3 H's here, so that's going to be 6 on this side, which also works out because the 3 times 2 here is also going to give me 6. So that is my balanced equation. And after this, we're going to get into some stoichiometry for our experiment today. So from trial 1, which is where I'm going to do my experiment from, I was giving, we had 14.28 milliliters of NaOH, and I'm just going ahead and write that in liters, but this can be found by doing the 14.28 and timesing this by 1 liter over 1,000 milliliters. So basically dividing this by 1,000 would give you the would give you the 0.01428, which I found here. So my liters of this is going to be times by my moles of my NaOH over 1 liter of NaOH. And then this is also equivalent to the molarity of the sodium hydroxide, so this is going to be 0.991, and since this is over 1 liter, that's why it also equals molarity, so this altogether would be molarity. So then I'm going to use this, and I'm going to times it by my balance equation. So I'm going to have my moles of NaOH at the bottom here, and to go back to my balance equation, it's going to be 3. So I'm going to put 3 there, and then on top here I'm going to have moles of my base, my citric acid. So as seen here, it's going to be 1. Okay, so then this figured out is going to give me my molarity of my citric acid, my moles of my citric acid. Okay, and then this is going to equal 0.004717. And this could be put in scientific notation, but for this case, I'm also going to use this number to find my molarity, so I'm just going to keep it how it is. So I'm going to go ahead and write this, and that is, like I said, my moles of my citric acid. And this is going to be divided by my liters for citric acid. And this can be found when we first received our lemon juice and we mix it with our water. So we had 27 milliliters, and if you put it through this formula, I'm just going to go ahead and put it in liters for this case because that's how you find molarity. So basically it would be 27 divided by 1,000 to find this number. And from that, with these two divided, my molarity is going to be 0.0175 for my molarity of citric acid. So this is the stoichiometry in order to find, using my liters and concentration of NaOH to find my molarity of citric acid. So from that, the next question that we're going to go over is determining the averages of our concentrations from the three titration cycles that we did. So this was from my my first one. I'll go ahead and write that out. And then I also had, for my second one I had 0.0179, and for the third one I had 0.0177. So basically we're going to add all of those to get 0.0531, and with this divided by 3, my average one is going to equal 0.011177 molarity of my citric acid. Alright, and then, so as these two were already calculated, and then that's the one I showed up there, so then this is going to equal my average of that. And then lastly, we're going to compare the averages of the pHs that we found. So my average, I already calculated it, but my average before the pH we took before the titration was 2.813, and then my right here before, and then my one for after was 8.713. So basically, to explain this, as the number decreases, the acidity actually increases. So by that meaning the lower the number from 1 to 14 for pH, the lower the number though it means it's more acidic. So when we did our titration or our neutralization, we basically took our acid and we added the base to it, so therefore it went through the neutralization process. So it's giving this a larger number because it's basically less acidic, and it's actually very close to the neutral point, which is 7, between 1 and 14, meaning that 1 would be the most acidic and 14 would be the least. So at the neutral point would be 7, so it's basically adding the base is going to therefore use the neutralization to make it, the actual solution, more neutral. And with that, as you can see, this one is very acidic, and this one is pretty neutral, meaning that with the base added, this is what type of thing happens. And to reference this lab report, I'm going to use my manual as a reference, and thank you for listening.